In this video, we're talking about a very unusual projectile motion problem. So we're given the launch speed and the launch angle for a projectile, but what we're asked for is the average velocity vector from t equals 0.5 seconds to t equals 1.5 seconds. So this problem is meant to get into the formal vector representation of position and velocity. So what we want to start with here is to represent the position of the projectile as a function of time, and then we should be able to compute that average velocity vector. And just as a quick reminder, a position vector, if I put my origin right here at the launch point, a position vector points to the location of the object at each moment in time as it's going through this projectile flight. So at 0.5 seconds it's pointing up here, at 1.5 seconds it's pointing over here, and everywhere in between that position vector is just tracing the projectile through its flight. That vector is rotating and growing over time to trace this trajectory out. So how do we find that vector that points from the origin to the position of the object at each moment in time? We can write this thing down in general as an x coordinate as a function of time times the I hat plus a y coordinate as a function of time times j hat. But we know the equations that describe projectile motion, and that will give us the x of t and the y of t. So x of t for a projectile is going to be x naught plus v naught x times t. That's constant velocity motion in the horizontal direction. And we know y of t for a projectile. That's y naught plus v naught y t minus a 1/2 gt squared, where g is the magnitude of the acceleration of gravity. In our initial position here, we put the origin right at the initial position, so x naught and y naught are both 0. Then I need to get my initial velocity components, and then I'll have my general position vector describing the position of this projectile as a function of time, and then we can get into this average velocity thing. So let's get the initial velocity components first. V naught x is going to be a 10 cosine 65. Into 3 sig figs, that gives me 4.23 meters per second. V naught y is a 10 sine 65, and that gives me 9.06 meters per second. And now I can write down my general position vector, and that's v naught xt for the x coordinate, so 4.23 t I hat. And then for the y coordinate, v naught y is 9.06, so 9.06 t minus half of g, which is 4.9, times t squared times j hat. Now we need a reminder of what the average velocity vector is, and that's a change in position divided by a change in time. We could also call that change in position the displacement of the object on this time interval. And that's actually a vector pointing from the location of this object at t1 to the location of the object at t2. And that's given by r of 1.5 seconds minus r of 0.5 seconds. And then we divide that by the time it took to get from point number 1 to point number 2, which is exactly 1 second. That's t equals 1.5 for the final time and t equals 0.5 for the initial time. And this average velocity vector points in the exact same direction as the displacement vector, but it's been scaled by a factor of delta t. And now all we have to do is plug in the numbers to the position vector, combine like terms for the unit vectors, and clean it up, and we'll have our average velocity. So first, r of 1.5. So I sub in 1.5 for t. When I do that on the I hat term, I get about 6.35 I hat. And then on the j hat term, I get about 2.57 j hat. Then I subtract the position vector that I get by subbing in 0.5 for t. That gives me a 2.11 I hat plus a 3.31 j hat. And then my time interval in the denominator is just 1 second. When I run the numbers here, I get 4.24 I hat minus 0.74 j hat. And to state my final answer, I really should have units on these. So these coefficients must have units of meters per second. So on average during this time interval, my projectile was moving 4.24 meters per second to the right and negative 0.74 meters per second downward. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, And best of luck on your math and physics journey.